Next time he asks me to fix the card. Oh, I'll fix it. It will be an interesting one.
So we're back with TiN doing another XOC lab video, or just engineering lab video in general for this one. So this we have, you've got like a scope hooked up of a current clamp, and what we're gonna show is impact of things like load line calibration on power consumption, and impact of the measurement difference between like a software voltage measurement for GPU voltage and then an external voltage measurement. Before that, this video is brought to you by Dollar Shave Club and their starter sets. Get your Dollar Shave Club starter set for $5 by using our link below, available individually for shave, shower, or oral care, or all together in one package. The kits can be customized to your needs with options including toothpaste and a toothbrush, hydrating shampoo, face cleanser and scrubs, body wash, or a razor with cartridges and shaving cream. Convenience is key, and care packages can be scheduled to send when you need a restock. Go to dollarshaveclub.com/gamersnexus or click the link below to learn more.
Yeah, that's one of the reasons why we implemented so much controls on the Kingpin card. So like you can play and find the best setting which fits your specific case, your specific game, or the benchmark. So it's not limited to only one setting which would be for everything.
And so it's going to be a dense video with a lot of information, but this is it's some good technical insights to the cards. We'll have a separate video on the physical hardware side of things, like what TiN does to get the cards up to the level that they can eventually advance them into like a KP design or something like that.
Yeah, pretty much some piece on, or oversimplified piece of the how we go through the design of the VRM and make the custom PCBs, including like VRM design and stuff like that.
Okay, so what is this demo going to be? What are we showing?
So that will show the load line difference and actually how the power is consumed by the card when the benchmark is running.
Okay.
So I'll have the Precision X1 open, where we can see the current GPU clock. It's just running on essentially no overclocking, and then all the power is maxed out and memory is not overclocked. So we can see the GPU temperature, and we can see the power on the drone from 12 volts from using this big probe gun.
Current clamp?
Yep.
So, okay, so let's talk about each of the lines here. So which line should we be looking at right now?
So
mostly?
essentially there are three lines here. We have voltage, the purple line, and then we have the yellow, that is the current from this probe.
Okay.
But to get the power, we actually need to multiply voltage by current, and that's what the scope is doing, and this is the red line. So we have readout, this is the RMS power, so this is more like average RMS current, average setting, and then we have the red, that is reported calculated power. So there are two values, one is maximum, one is RMS. Maximum is the peak power, and then RMS is average.
All right, so right now we're just idling.
Yeah, we're idling, and because this is XOC bias, we don't want to have power capping for this illustration. So we can see the power is actually quite high, so it's 90 watts RMS. And when we start the benchmark, and the benchmark is 3D Mark TimeSpy, just GT1 test. But the similar happens with any benchmark, just the different levels.
Okay. And that's something we've noticed with TimeSpy Extreme, for example. When I was really desperately trying to get more power out of just chilled cooling, I would do hotkeys for increasing the frequency based on the load level of benchmark at the time.
Yep.
And so for that, we kind of noticed that with like GT2, there's certain scenes where you'll see the power consumption spike maybe 40 watts or something.
Like if you actually really benching for the best score, you would have the voltage and frequency can apply in the using the profile in the precision. So you can actually run one part of the benchmark with the one level, and then another part of the benchmark with different frequency and voltage levels. So that's why you can maximize your score in the benchmark. But like especially when you run in LN2, you need to handle the LN2 container and you need to apply the settings right time. And often if you apply the settings, then benchmark can catch it and will crash out back into the window. So you cannot do that for every benchmark.
Right. So what types of, what's happening in the benchmark, I guess, or what kind of load is being applied to the GPU where you do see those spikes? Is it like indicative of an increase in memory utilization, or?
Well, the power we are measuring here is 12-volt input. So this is essentially the complete power taken by GPU and by the memory together.
Okay.
But most of the contributor is, of course, GPU. Memory, I would say maybe like 20% of the total power that goes to the memory.
We're looking at power before the VRM too with the clamp, is that right?
Yes, yes. So there is also efficiency effect from the VRM itself. So like within the modern VGA card can run around 90% efficiency. So 10% actually power is dissipated into heat by the VRM controller. And there is also some drop on the traces, but that would be like a couple percent when the power is delivered from VRM point to the GPU die itself.
Right.
So right now we are running with the load line at default. So we can check that level 10, that's the default pre-program voltage. And the power reading is around 420 watts maximum, and then around 300 watts in the average. So I can stop this capture. And we can actually see, you can guess, like the waveform is very repetitive.
Yes.
So like you can almost count actually how much FPS you have running the benchmark just looking at the power. That's why like using the scope for this kind of measurement is very good illustration, as if you just use DMM, you see just the number which is average, and you don't see what's the peak or what's the low power.
What does the waveform look like that's actually making the number you see on the screen?
And when you run the benchmark, which is have lighter load, then of course this frequency will be faster as well, and that peak and transient of changing power will be faster. So like it's important to test on both low loads and high loads.
Right.
So we had 430 watts or 300 average, and this was with the default levels. And we can also run it again to just take a look on the temperatures.
2080 Ti Kingpin card, so you're able to tune it a bit.
Yes, we have extra controls. We can play with the load line. We can play with the different VRM settings to fine-tune not too much power, so not too much heat, and also enough voltage for GPU to run the maximum frequency we can get. And the power is important because it have direct correlation to the temperature GPU is having. So like we can see, like idle is 33 C. This is all-in-one water cooler. It's essentially the same as Kingpin is shipped, a retail cooler, just no cover. And we can keep an eye on the...
So we need to hit run again on this? Or you leave it paused?
Well, we can run it. So the power is about the same, and temperature goes like 40 C. This is XOC bias, so the frequency is a bit lower. But we can see like this, like around 40 C. And we can see how that changes with the different load line. So I can run much slower time scale. So we can actually see that in the recording view. So you have the power, current, the yellow is the current, and then when the benchmark stops, you go to the idle condition. And then when we start again, but let's say we use load line level 4.
So that was level 10.
Yes, level 10 is the default settings for Kingpin card. And we can run the same test again.
And then just to clarify for the audience, the closer you get to 0, I guess the more aggressive the load line is going to be.
0 essentially GPU will get what you set the voltage if you measure directly at the voltage stance points. If you measure at the probe point from the connector on the PCB, it will be still small difference, and we will talk about that in a minute later.
Okay.
So we had 40 C before, and we'll run a little bit longer. So I'll go back to the fast scale. So we can see the power. And it's 460, 465, and 308, 305, around 300 watts.
Right.
Average. Temperature is a little bit higher, 42C.
Power consumption is a little higher.
Yep, it's 475, 320. So it doesn't look like much, but actually when you do, if you overclock higher, and especially when you apply higher voltages, you will see much bigger difference.
So the only thing that's changed between this test and the one we just did is the LLC. Okay.
And we're already 3C hotter.
And we came down from, okay, so we came down from level 10 to
level 4.
Level 4. So that's a pretty immediate impact then. That's very noticeable.
And then we can do the same thing with level 0. And run the same test. So there are, for every piece of silicon, be it GPU or CPU, like there are 3 main factors that affect it and link together. That's the power, temperature, and the voltage. So if you have changed even one of the conditions, then 2 others will change as well. So that's why even if we chill this GPU to, let's say, 0C using the liquid nitrogen container, the power will be also lower, even the same load lights and the same voltages.
Right. Straight like 480 now? 480 watts?
Yeah, it's 490 peaks, 488, 494. And we're running level 0 now. And then you also see the little bit difference on the power, depends on what part of the benchmark is running.
Right.
Because some pieces of the benchmark actually stressing more on the shaders, other pieces maybe like using RTX cores. This is not the RTX benchmark, not the Port Royal, but there's still a lot of different units inside the GPU that work together differently. So we are up to 500 watt peak, and the power was, I see, like 320 watts or so.
For average?
Yep. And then we're around 44C. And if we set voltage to the fixed level, let's say 1.2, then the card shut down. Okay. Because I didn't disable the OCP.
So we just hit a NVVDD OCP, I guess. Is that what that was?
Yep.
Okay.
So we can just set the reference line, so we can easier to compare the difference between the load lines.
That'll help.
And
okay.
This will be the line A is 0, our 0 reference, and then the B is 23.7 amps. So you will need to multiply that by 12 to get the power reading. So the benchmark is over, and now I can set to level 0 and run the same thing again. So you can actually see like different parts of the benchmark, like how the power changed.
And so we're in slow mode now. That way we can actually see the differences.
Yeah, the whole this one block is 20 seconds, so the whole screen would be around 100 seconds. So, and you can see already power is
much higher.
Level 0 is...
So that's a good illustration then. So was that level 10 versus 0?
Yes.
Okay. And so we're at, your reference line is 23.7 for B?
Yes, and then 23.7. There we go. And power now is become 37. The current reading is around 37.2. So that's just from the load line. And then there's the temperature.
Right? 27.2?
Yeah, 27.2.
That's a pretty big increase. So a little under 4 amps increase just from changing only the LLC, nothing else.
Yep. Because what happens is when you change the LLC, the real voltage that delivered to GPU changes as well. And when you have more voltage, you have more heat, more power. This line is 0 watt.
Okay.
And then we have the first test, which load line 10, that was 284 watts. And then in the end of benchmark, it dropped to like 263 watts. That is RMS reading. So that's not the peak reading, because on this scale, we don't see the peak readings. It's like too small to see. Right.
Would the peak readings sort of just follow the same trend? Or is there any more significant, like is the...
Well, the peak, they happen very fast and very short, so they will be actually, you will have much higher and much lower, but on average, like you can like scale them up. So, and the peak with the load line 0 was 340 watts. So we have difference between 280 and 340.
Right. Which is also putting you closer to, like if you're working with a card that has power limits,
yes,
then that's a consideration of if you start lowering the load line or you know, running a more aggressive load line,
yes,
burning through your power allowance.
You will run into the power limit earlier and your frequency will be actually lower, and that's why what you see in the end result as the lower benchmark score.
Right.
Even you would expect like, okay, I have more voltage, more frequency, but the score is worse. That's one of the reasons.
Okay.
That's another reason why we are running actually XOC bias, which doesn't have the power limit, because it allows us to just see the effect of the load line without being capped by the power.
Right.
Because otherwise we would see different load line, but the power is the same because it's all trimmed by the bias and driver settings. I think I can show one short thing.
Okay.
It's essentially take the reading on the card. Like because even like on EVGA OC forum, we see like some people connect the DMM to the probe connector, and they see difference between readout on the DMM, readout in the precision, and also readout in other hardware monitoring tool like hardware info or GPU-Z, and like why is that and where it comes from.
Right. So you want to do a manual measurement for that?
Yeah. So I'll get the DMM in. Got my proper riser. That's the real high-speed one, which like certified and everything for the PCI Express. So see the shielded coax wire.
I know there's like 3M ones that are supposed to be the best or something for like consumer
Yeah, well,
use.
this is a real deal. This is actually 3M is actually very good, and for the PCIe Gen 3, that will be like the one which I would recommend, and it's still reasonably priced, I would say. Like around 100 USD if you use by 16.
Right.
And this one is around like 350. So this is Semtech.
What is it?
Semtech. The
Semtech
company, they specialize on high-speed interconnects, like the backplane connectors for those blade servers.
How hard is it to clamp like the PCIe, or sorry, the 12 volt lines coming out of the riser? Do you have to like split them out if you wanted to clamp those?
Yes.
Okay, yeah.
Essentially, I would need to do the same as here. So I have the ground bypass, just go directly to a card, and I connect only the 12 volt wire. So maybe we can actually talk about that in a second. So essentially, how the current measurement works, you use the big clamp probe. You can buy, this is the probe for the scope. It's rated for 150 amps. But there are also like DMMs, which are made like a clamp. So the probe, this probe is for the scope. It's designed to interface and read out with the current with the high speed. So that's why it's like so bulky and big. But
are you clamping the 5 volts in there too, or just 12?
No, this is just 12 volts.
Okay.
3 cables from the power supply going to the card.
Okay.
And like if we want to have 100% accurate measurement for the power, we would also need to have clamped the 12 volt coming from the PCIe slot. But because on the KP card the power input is not drawing much power, for the sake of the demo, we omitted that.
Right.
Otherwise, I'll need to cut this wire and run through the clamp as well, or use another clamp, connect to the second channel on the scope to measure the both. So what I want to show here is how the voltage changes, depends on what settings we applied. So we have the reading from the precision, which is this GPU voltage. It reads 1.172 volts. This is, we're just idle in the 3D mode. And then we applied 1.15 to the VRM controller. And I have the DMM hooked to the probe connector. This is just reading NVVDD, doesn't read anything else. So we read around 1.134.
Okay. And then what is the, okay, so 1.134 versus
1.15 and 1.173.
Okay. And it's all supposed to be the same thing ultimately, it's just different places of being measured, I guess?
Correct. So the difference comes from how the measurement is done. So reading which we see in the precision is taken by the hardware monitor, and it's pretty close to the GPU die itself. And that's like a reason why we see the higher voltage, because controller compensate for the voltage drop on the PCB and on the GPU connection, and we see essentially voltage closer to what's actually GPU getting. And reading from the DMM is a little bit lower as it reads from the VRM side.
Okay.
And setting is somewhere in between, because we are just idling, and it affects also for the load line. So the setting is just fixed value for no matter what load line you have.
Right.
So if I run the same benchmark, 3 mark times by GT1, then we can see how these voltages also change. I have illustrated the differences in OC guide for the Kingpin card. It's public on the xdevs.com guide section. So there are a little bit more details on that. So we run GT1 in window mode, and we keep an eye on our voltages.
So what's the most realistic or practical way to get an accurate voltage measurement? Like, out of all these numbers, what do you trust the most, the DMM or?
I would trust the reading from the precision.
Okay.
Because actually we spent some time to fine tune and make sure that voltage as close as GPU actually gets as possible.
So does the fine tuning only apply to the EVGA cards, or I mean, if I plugged in some other card?
I think it applies universally, but
okay.
Like the level, how much effort is actually engineers put into that aspect is very lot, because you, like in the normal condition for the everyday user or gamer, like you don't really care about, oh, my voltage is 0.1% of what is actually set. So you don't even know the voltage most of the time, because you cannot monitor it easily on the reference cards. There are no, like, yes, you can connect the probes, manually probe the points, but you also get the different voltages from, depends where you measure that. Like right now we are reading, benchmark is running, and we're reading 0.105, and you can see the voltage in precision actually higher.
Yeah, so we've gone between, well that's, so going back to idle, still 3D clocks I guess, but idle 1.13, and then when it was running, it was like 1.1 or yes. 1.05 or something.
1.05, and that is with level 10. So we have the most load V drop now, and we can change the load line and see how that changes as well. So you will see less difference in the voltage change from the precision readout than actually from the DMM. Because DMM is more like VRM centric, and the reading in the precision is more actually representing the die voltage.
Core centric, okay. So 1123, 1.05 on the DMM.
And now I can set level 0.
And now you've gone 1220-ish in precision and 1.25.
So they both the voltages goes up.
Sorry, 1.125, yeah.
Because on level 0, we are actually overcompensate for that.
So that'll cover us for the voltage demonstrations, the LLC demonstrations. I think TiN was worried that we were starting to look like two old men sitting down, so we've decided to stand again. This definitely was not shot out of order. That would be weird. So thanks for watching the video. Subscribe for more. Go to patreon.com/gamersnexus to help out directly. And check back for our other content with TiN. TiN, thank you for joining me.
Sure, no problem.
We'll see you all next time.